Hello and welcome back. Sorry. It's Friday. It's Bayes. What could go wrong with something like that, right? Friday and is made for Bayesian, isn't it? Like, especially on a day like today, rainy and drizzly outside. Why not just stick inside and work on some priors? Something like that. That's not going to work. I need a screen. There we go. Okay. So start off with some announcements. Homework 2 is available. Did the icon homework assignment show up in your icon? Oh, thank goodness. I just wanted to show you what it looks like and talk briefly about it. And as you might expect, it's, well, I saved it as a markdown file. This is not what I wanted. Let's go to teaching. Here we go. So the idea with it is the following. You're learning in this class about how fun Stan is so far. And that may sound like sarcasm. Maybe it is sarcasm, but the idea is, with Stan, many of you, by the way, may have taken a course from Lisa Hoffman where there's this cool online homework system that checks your results, right? We can't use that in this class. And the reason for that, I think I mentioned before, is everybody's going to have a different type of code. If you change a little bit, permute a little bit of your code, the random sequence of numbers gets thrown off, so we can't do that. So this is my closest attempt to doing it. Everybody has one file, everybody has one homework. This is a homework that if you were in Lisa's intermediate class, come on, there we go. If you were in Lisa's intermediate class, you would have seen this homework. I think it's homework 6. It's about Scrabble. She tells a story, yada, yada, yada. There's always a story with every one of her homeworks. I'm not as interesting, so. The basic idea is this. I made this markdown file. And I'm going to ask you to put your answers and your syntax in the markdown file. So if you've never used R Markdown, let me know. You have not? Never done that. Oh, I'm not sharing the screen yet. Do that too. Sorry, people online. There's your screen. So an R Markdown file, let me give a brief intro to R Markdown. You use it with RStudio. It will install a few packages to make it work. I'm less concerned about what it looks like, because what happens is you hit Control-Shift-K in RStudio, and it does what's called knitting. It uses a package called knitter to create what you see on the right. I'm less concerned about what's created on the right. I'm more just trying to organize the documents so I can try to efficiently grade them and put comments on them. So in the R Markdown file, it's basically, have you ever used any type of Markdown document before? Markdown documents, if you ever use a Notes app, like in OneNote or Notes on iPad or Mac, there's this style of writing called Markdown that tries to make writing quick. You can easily emphasize things or otherwise. In fact, go away. With RStudio, there's a Markdown quick reference. It talks about how you can write text. So basically, you just write plain text, and it tries to and make it really quickly into something that's like HTML or Word or PowerPoint or whatever. So the key thing, though, is in Markdown, there's this section here for each of the questions where I have a set of questions. Now it's gone. And I have a spot that says my answer. It looks like just bold, but if you go to the text, it's right here. So the answer, what I'm asking you to do there is you can put your code that does the analysis somewhere in the document. To put code in, you put 3 tick marks backwards, a brace. You tell it what type of code it's R, and you give the label, my section, my block, or something like that. And you end it with 3 tick marks. And then everything that's in that little section right there will be run in R. And then you can see it and write about it afterwards. So if you wanted to talk about mean of R let's say we have 1,000 people, we want to look at the mean for it. Okay, the mean is 0.01. You can run the R to get that number out of it, but then you can just type about it. The answer is 0.01, something like that, right? So there's more fancy ways of doing it. I don't need you to go and refer to the actual R object. Like, for instance, you can do something silly like this, my mean, and you could even do this, my mean, I think. That might not do it, though. Anyway. There's a way to refer to it. I've forgotten it now off the top of my head. I'm not looking for you to refer to it dynamically in the document. It's more just give me the answer. But the goal is to, where you see this my answer section is where you start typing. So let me go a little bit further into the homework. The homework is basically this. We have a linear models problem. Actually, there's a story. There's a data set that has the outcome, which is the number of points you got in a Scrabble game. There's, by the way, Scrabble, for those who haven't played, is an old English language board game where you try to spell out letters that you have in your hand, spell out words with letters you have in your hand for points. The bigger the points, the better the score, just to set the frame. There are several variables. Verbal ability variable, a spatial ability variable, because you have to sort of figure out on the board where to put the words. And then whether or not the person that you're playing is an easy opponent or a hard opponent. And later on, when you start answering questions, I'm asking you to report a few features that we already talked about. So whenever I ask you for an estimate of like a slope, that estimate, what I'm really asking for is the posterior mean, the posterior standard deviation, and the 95% highest density posterior interval. Do you remember those terms from last time? Posterior mean, mean of the chain. Posterior standard deviation of the chain. And the HDPI, highest density posterior interval, is the interval with the narrowest window that contains 95% of the density of the posterior distribution. I also give you some instructions for how to run Stan, 4 chains, a warm-up of 2,000 iterations, sampling of 2,000 iterations, and uninformative priors for all model parameters, but you can pick those, including Stan's choice, the default. So I'm not going to argue with you about priors because I hate those arguments. Okay? So what are we doing? The other thing, key. I encourage you to work together to build the answers, but I want you to have your code be your own and your text be your own. So you can talk to each other about like, I'm trying to do this and it's not working, and I'm trying to do this and it's not working, but have the code be on your own. Because my goal is, I'm trying to simulate a collaborative environment, but I also want you to gain the skills on your own as well too, right? So just don't copy each other's answers for text. That's the main thing. With the exception of the end. The last question says write a results section. And I actually copied and pasted Lisa Hoffman's results section. And you can use that, and it will look very similar to each other's. So that's the one exception to that rule. Okay, backing up. What do I ask you to do? Any questions so far? No. I literally confirmed with her that I could rip off her homework. By ripping off, I mean copying. I meant to do this because those of you who've had this homework before, it'll give you a perspective of the comparison of like what happens in ML versus not, or at least squares versus Bayesian. But I ask you a question, I tell you to build a model with linear effects of component type, verbal ability, spatial ability. You'll have to talk about then in model 2, the interactions that show up as well. And the questions are all about details, like what's the slope, what's the interaction, what's the intercept, yada, yada, yada. I cannot give you anything to check your results, though, because again, everybody's going to be a little bit different depending on your choice of prior or depending on how it works. So I will say this. If you would like to show me, there's basically 2 analysis models and a bunch of questions about them. If you'd like to show me your analysis models before you get too far down the path, I encourage you to do that. Just shoot me an email with them. Hey, I was going to do this for section 1, this for section 2. Does this look all right? Do that, because the problem is if you don't specify the model correctly, then all the stuff that you're writing about will not be the right numbers. even if it's the right things that you're writing about. So I just encourage you to use me as your homework checker, okay? It's not as efficient as a green box or a red box that you used to have in some of the classes like Lisa taught, but I'll be your green and red box, sort of. Maybe I'll write my reply in green. No, never mind. So that's the deal with homework. Any questions on that? Oh, and a question about data. The data is also available online. So the data are right here. There's a data set. Everybody gets the same data. It's all right. That's data. Never mind. And of course, I just closed it. All right. I'm sorry?
It's on the icon.
It's on the icons. Okay, great. The data are on icon, and it should be on my site too. But there's an Excel file for it. Oh, there it is, right here. Data file is right there, underneath there, and a link on icon as well. Okay. So just one. Everybody's got the same data set. Now remember, even though you have the same data set, you may not get exactly the same results, because if you specify a slightly different prior, that'll be different. If you don't set a random number seed, or if you set a different one, that'll lead to different results. And if you're using a different type of operating system, that could lead to different results. So if you're like, my numbers, like the intercept, I'm just throwing a number out, I don't know what the scale is, I don't remember what it is. The intercept is, let's say, 147.6 on your machine, and on someone else it's 147.7, don't sweat it. It happens, okay? It's more, I'm going to be looking for, is your model syntax correct, and then are your interpretations correct from there? That's the bigger picture. And unless, yes, we all are always worried about precision in results, but given your model code, I could always replicate your results, I know. So that's the key thing for me. So, sound good? Other questions on this? Also, I see a comment online, and I actually didn't know that. To create a chunk of code, you can do Control, Alt, and L. Let's see what Alt is. That didn't do it. Nope. CMD.
I, not L.
Oh, nope. What was that? I'm sorry? Oh,
I think it's I.
I, not L.
Yeah.
Pardon me. There it is. Yay, there it is. Control, Alt, I, and on Mac it's Command, Option, I. That creates your chunk of code for you.
So is the code reading inside the bracket?
Inside the bracket, and that's right. So, and if you do that right there, that's where you put your code with. And so anything with the 3 ticks inside there will be our code. And that's where you can do your analysis itself. And for whatever reason, if you can't get it to work, either contact me or just write your R code in a separate file and attach that to. There are 20, 21, I think, enrolled students, so it may take me a little bit of time to read it all, but most of you will probably be able to do it one way or the other, but I'll work with you if you can. It's no big deal, okay? Yeah.
Is the supporting example documentation essentially that diet stuff?
That's right. That's right. Yep. And what is going to be presented, at least in the first lecture next week, if I get my act together and put it together. That's right. Okay, other questions? Okay. Does this look daunting or doable? Hopefully it's doable. I'm not trying to challenge you. I'm just more, this goal of this homework is to get you working with Stan with one linear model. But remember it doesn't sound like psychometrics, but remember that's like one item for like a factor analysis, right? So the psychometrics is coming, and this is knowing how to do this is the first step to knowing how to do the psychometric models. So that's where this is sort of building upon itself to make it work. And then I can try to also add on to your experience with linear models as well too. Okay, we're good on that. Next week, yeah, question?
I'm just wondering, so you're saying that we may get a bit different results. Is that because we're not doing a big enough, would we have to do more iterations?
Yes. Yeah, I mean, it's the numerical sort of, it's the random number sequence and its practical number of iterations. Like if you ran it 100,000 iterations, you'll get the difference in the results should be very close. Sorry, let me check that. Let's imagine you write your model, and you take your code and someone verbatim uses it, which is not supposed to happen in this assignment, but let's just say it does, right? But they use it on a different machine. Like you send me your code and I run it on my Mac. If we ran it 100,000 times, it might be the 4th decimal place we'd like to see the difference.
Okay.
All right, but the longer you run the chain, in theory, it should get to the same spot. It's just, you could be waiting forever for no reason. And what I'm trying to do is the smaller number of iterations is good for the planet, right? I'm just kidding. It's less in energy. Sorry. I'm thinking about my carbon footprint in days, and it's not good, as I said that. But no, thank you for your question, though. Okay. Other questions? Okay. Finally, actually, 2 other things. Next week, I'll tell you more about the project. I'm trying to make it, so here's the struggle with this class. As you know, it's like I have to sort of teach you the Bayes and teach you the psychometrics and then put them together, right? So I want to make sure there is a project that I'd like you to use that to practice on data that may be familiar to you if you have it, or something that's a little bit more unique than just sterile examples. So there will be a project, but I might just scale it back a little bit, sort of expectations. So we'll talk about that next week, okay? It won't be, it'll basically, we'll find a way to make it work, okay? And then finally, I have some good news for you. Maybe not for me, but for you. How would you like a week off of class before Thanksgiving? So I have a conference to go to in the middle of October, and I'm like literally just got off the phone with the hotel with Lisa. Actually, we're both part of this society that does this conference, and we're sort of unofficially sort of running it, at least the logistics. So I will not be accessible or at least not be available for class to teach class on October 12th and 14th. Just tell you now, put that on your calendars. We will not be having class those days. And because I'm trying to recreate what I do, I don't even have videos or something for you to watch. They'll be like, I think that might be where you can work on the intro part of your project, like the proposal part or something like that. So we'll make that. Just putting that as a heads up. So yeah, you don't have to hear me for a couple days. Even better, right? It used to be, I used to say, education's like the one product that the consumer wants less of. Yeah, but that's it. So those are my announcements. Any other questions that you have or anything that you'd like to talk about before we dive into the example again? Yes?
So for your project, because I'm from a different department, I don't do psychometric.
That's okay.
I use an experiment data.
We can find a way to make whatever you have work for you. Yes, absolutely. And and that's the thing about it. I wanted the project to be a chance for you to practice this with your own stuff. And if it doesn't exactly fall in line, psychometrics is a broad enough field that we can pretend psychometrics applies to each, okay? And that applies to each of you as well too. If you have data that's not exactly what we're trying to do, we'll find a way to make it work. There's lots of ways, depending on the structure of your data, to sort of fit under that. So, turns out there's a big connection between like psychometric models and multi-level or mixed models. So if you have like repeated measures data, we could pretty much pretend that's psychometric somewhere too. Okay? How's that sound? All right, I say that, and I'd like to get to it in class, but again, I'm teaching the Bayes stuff, and then I'm teaching the psychometric stuff. When we actually get to CFA, it's going to be boring. It's going to be all the items are normal, just like the end of the syntax I left you with here. Remember model 1? You're going to see this for every one of your item responses. And then there'll be an additional code for the latent variable or the latent variables. But that's basically it. So once we get to once we do all this stuff and we get to CFA, it's small modifications of syntax, some big modifications about how we check model fit. I haven't even talked about that yet. That's next week. And then, then we're done. It's like, oh, look at that. That's CFA. What's IRT? Oh, it's not normal anymore. It's Bernoulli. Okay. So it's small modification in syntax again. So when we get to, the way I'm trying to structure this is when we get to the psychometric models, which sound a lot more complex and everything, to actually implement them, they're not as hard, or at least they build upon what we're doing now. And then it's more, what do they mean? How do we interpret the results? How do we check for the things that we need, like model fit or quality of items or other things that go for it? Okay? Okay. Anything else? Oh, got a question online. We might get to this in the example, but is r squared equal to sigma squared when looking at the summary table of chains in MCMC? I'm not sure I understand the question.
So I was looking at the homework and I was trying to, one of the questions is to talk about like r squared. So I didn't know how, like, which value corresponded to that from the table.
We will get to that.
After I typed, I realized that my question didn't make any sense.
No problem. No problem. We will get to that. It's not exactly sigma squared, but we'll talk about that as we go forward. All right. Anything else? Okay. You remember where we left off? I do. I left you with the cliffhanger. I'm going to run all this code to this part. Actually, no, because it took a long time to display this. Yeah, of course, that's a problem. Let's do this. All right. You'd think I'd know how to do this by now, right? All right, here we go. We started with, what is going on here? There we go. We started with our linear model. And we had this linear model on our diet data that gave us a summary that looks like this. We interpreted all those parameters. And then we said, okay, we're going to go and take this and put it into Bayes. So we put this into Bayes right here. We compiled our stand program. Ironically, compiling sometimes takes longer than it takes to run the chains itself, like that. And then we looked at the summary of this. We found that the largest R hat, remember R hat was our convergence diagnostic. We want it to be close to 1. The largest R hat was very close to 1, so this looks like it converged. I'm not going to plot those. They take a while. But I left you with this comparison of values that we got from least squares, the first two columns, and values that we got from MCMC, the second two columns. And we noted that for most of what we see, the estimates are fairly close, within at least a decimal point, right? 0.05 or so. But the standard errors were always lower in least squares than the standard deviation was in Bayesian. And the standard error and the standard deviation are somewhat analogous quantities. They're characterizing the uncertainty that you have in an estimate. For us, Bayesian, it's from a posterior distribution. From least squares, it's from asymptotic convergence. There's a formula for it. X, or sigma squared times x transpose x inverse is the square root of the diagonal of that thing is that. Anyway, giving you too much information. And I left you with the question, why is the standard error smaller in least squares than in Bayes? Did you think about that? So let me give you the backstory to why I'm asking this question. I've done Bayes a lot. I started to give a Bayes lecture at Kansas, and I just on the fly did something, and I'm like, oh, wait, that's different. I thought with flat priors that Bayes and maximum likelihood, or Bayes and least squares in this case, least squares and maximum likelihood for linear regression give equivalent results. So I sort of intermingled the two. I thought they were the same. What's going on? Turns out, anybody have a thought on that? I should back up. Anybody online or anybody in person? Why do we have smaller standard deviations in least squares than we have in our Bayes estimates? So I'm going to tell you. So again, in least squares, we don't use a sampling approach to the posterior. In fact, what we do is we try to estimate the residual variance, or the sigma in this case, standard deviation, and the fixed effects, or the model parameters, the regression coefficients, all at once. And then we go and say, well, what's the standard error of our estimates? And the way we find our standard error, I was mentioning this before. Really? Come on, Apple Pencil. Was the following. You remember I left, I don't know that I described. Did I describe the model matrix at the end last time? Maybe I did a little bit. I think I showed that. If we put our model matrix into a matrix X, and I'll put a little half arrow over it to say it's a matrix. If I do a matrix product, which I'll talk about later today, and I take the matrix inverse of that, if I take the residual variance, multiply that, that right there is a variance covariance matrix of our parameter estimates. So you're like, okay, what's the variance covariance of the matrix? So it's if we have 6 parameters, this is a 6 by 6 matrix. The diagonal of that is the squared standard error. Right? It's not the standard error, it's the squared standard error. So we just take the diagonal of that and get our standard error. But 2 things about that. This quantity comes from asymptotic convergence. We can show through like theorems, a little bit of evidence, that, and proof mathematically, that as n goes to infinity, again, the basis of frequentist statistics is n goes to infinity, our parameters, that's not what I was looking for. These parameters right here converge to a normal distribution with a standard deviation defined by that standard error. Okay? Standard error. So the key, though, in this is this term right here. It has a variance. In maximum likelihood, there's one value of the variance. It's the maximum likelihood estimate, or in least squares, it's our estimate of residual variance. We can calculate it by, for each person, forming a residual value and then going and calculating the variance of those residual values, right? However, in Bayes, we don't have one value. What do we have? We have a posterior distribution. In fact, now I will show this. There we go. So here are all the values of sigma squared. Right? So as our Markov chain is running along, each iteration will have a different value of sigma squared. Right? I can even show that in the trace plot here real quick. Maybe? You can do it. It'll come. I learned that last time. Patience. Patience. Okay, never mind. Maybe it won't. R just flat out ignored me. I feel like a dad, like with my kids. So, yeah.
That was really funny as a parent. But anyway.
Did you listen to me, Hugh?
Sorry.
Yeah.
For the sigma, so you're saying that, I just want to make sure I understand.
Mm-hmm.
So the least squares is taking that highest part of the distribution in the sigma.
That's it. It's putting in one value.
Whereas Bayes is using all of that distribution.
That's right. At every step in the chain, there's a different sigma. And every step of the chain, the different sigma, actually, the way that this sampling works, because sigma is simultaneous being drawn to the other parameters, right? It is wiggling around. That's causing some wiggle in the other parameters as well, too. Right? In fact, if you think about it, sigma squared is actually yoked to these other parameters. Right? If you think about yoked, what do I mean? They're tied together in a weird way. Sigma squared, or sigma, right, is the standard deviation of the residuals. What is a residual? Your observed value of y minus your predicted value of y. And your predicted value of y depends on all the betas. So the betas are wiggling around. So if you change where the betas are, you change the location of sigma, right? The further off the betas are, the bigger the sigma happens to be. Likewise, when we get into what the algorithms are, which I'm still trying to figure out how I can squeeze that into class, like Gibbs sampling, we can easily show this. We tend to block parameters in these models, meaning we sample this one conditional on the current value of all the others. Or we might sample all the others conditional on the value of sigma. And actually in Gibbs sampling, and for linear models, that's where it works most efficiently. So you try a sigma out, and you grab it from a random distribution, and then conditional on its value, you draw the betas, and so forth. And so why this is different is because sigma is wiggling around, effectively. Sigma is wiggling around, though, in part because of all the parameters are wiggling around. And so what's happening is uncertainty in our analysis is really much more represented in a Bayesian approach, I feel like, right? When I look at a bigger standard error, what does that mean from an analysis point of view? Let me get back to, yeah, I had it right here. Right, if you're trying to be thinking about whether or not this two-way interaction is significant in the least squares sense. Now that's significant, that's a least squares type of term. The Bayesian version of that's a little bit weirder. We would look at a walled test is what we would call it, right? This parameter divided by the standard error should be standard normal, something like that, right? So the smaller the standard error, the more likely it is we reject, right? So if you were to compare it, like again, this is sort of mixing modes, and I don't want to do that too much, but I just want to make a comparison. If this standard error were here, we'd say we actually have less power, right? We have less information about what we're trying to do. And that's the part of Bayes which is really interesting to me. Because we're representing our uncertainty in our analysis in these sort of yoked parameters, what the result of it often happens to do, at least when I think we're doing it correctly, is a more conservative approach to the error itself, right? Because, and I'm going to show you it's sigma in the next set of models I run. But because sigma's wiggling around, makes all of our parameters a little bit more uncertain, that I think is a nice thing, right? We have 30 people in this example here. The variance, the sampling distribution of a variance with 30 people is kind of wide. If you were to put a confidence interval on the variance for it, it'd be fairly wide with 30 people. It's harder to get a variance. Like a sampling distribution for variance is wider typically than that for a mean. So why I'm saying all this is one of the features of Bayesian that I want you to think about is this uncertainty representation sometimes leads to less power, although we don't think of it that way, but less ability to sort of distinguish things. What do you think about that? Least squares is lying to you? No, I didn't say that. Any questions on what I'm saying here? Yes.
I kind of hung up on something you said about if the standard error from the OLS estimate was in the Bayes, we would have less power.
No, actually, hold on. Let me see. I probably said that wrong.
Okay.
Let me go to this next part of the code real quick and see what I was really trying to say. In my next part of the code, I'm going to plug in the value of the standard deviation. Where am I getting this from? I'm getting it from the full model, that's right. If I go back all the way up here, it says the residual standard error is 7.949. So if I will go and plug that into the model, I want to show you what the results look like. So I want to basically pin down that the idea that part of the reason our results are varying is because our some of the parameters that don't typically vary in ML are varying now, and that one of them being the standard error.
So basically the first model that we estimated last time is basically we weren't putting any constraint on it.
None.
Okay.
Now I'm just trying to see exactly if we can sort of replicate our least squares or ML model a little bit differently. So I have to recompile the stand program because I put a new number in there, it changed. And also, I'm sampling a ridiculous number of values because I want the precision to compare the decimal places. So I have 100,000 values here for it. So here is our summary. 100,000 values are there. Well, look at those R hats. Again, it converged. First thing we always check is convergence. don't want to be talking about it. Look at how ridiculous that number is. It's good, right? Ridiculously good. But the thing I wanted to compare was the values that we have for the fixed effects here. So the difference between these two models, make this a little wider. The difference between these two models is I went and I set the value of the residual variance to what we would have assumed it to be or found it to be under least squares. Or another way of thinking of that is I put it to its most likely value. Because least squares and maximum likelihood are the same. Look what happens when I do that. Standard error here, 3.007, 3.011. We're off by 4/1000ths of a decimal place. Real close. Negative 3, or here, 0.4586, 0.4587, right? So you can see the numbers are lining up almost identically here. So the key in thinking about this, and not only are the numbers for the standard error and the standard deviation, but the estimates are as well. So what am I trying to show you here? That in our conception of what regression models happens to be when we're using a most likely estimate for a lot of our parameters, sometimes if we were to go and not use it, we're to let it vary a little bit, we'd see wiggle in other parameters as well too. And that's the Bayesian approach to how we do things. The MCMC algorithm itself allows the standard error to vary. Right? It's trying to, it wants it to vary. It wants to see its posterior distribution. Whereas in maximum likelihood, we don't care if it varies. We want it to be the most likely value, something along those lines. So the reason why we saw in our first example larger standard deviations was because we fixed the value of sigma squared, or we didn't. We allowed it to wiggle, to move around. And as it's moving around, it's implying more error effectively in all those parameters where it's used to how it goes. So here's the fun thing about it. As n goes to infinity, though, the Bayes estimate from the first one, right? If we think about what happens to our density, what will happen to our density as n goes to infinity, come on, you can do it. Maybe? Anyway, the standard error, right, the wiggle in sigma will become smaller and smaller and smaller. Right? And as we just saw, I'm muted. I shut this off. Like sigma is a flat line for this analysis, right? Whereas if I had like n of 100,000 instead of n of 30, we'd pretty much see a flat line. It'd wiggle, but it'd be wiggling very little, right, in fluctuation. So what does that mean? Right? We would expect to see very close to the same standard deviation. The posterior standard deviation and your standard error would look the same with a really big n. And so this is the concept I want you to think about. That Bayesian, when we do Bayesian statistics, we aren't just assuming that n has gone to infinity, right? We are sort of allowing n to be somewhere below infinity because the way we build and estimate our models allows for that uncertainty to be in the process, right? The least squares estimates that you see in this box right here above us, this side, assumes that n is going to infinity. This is the asymptotic convergence. Right? This is assumed. Whereas in the Bayes world, although this is from the second model, if we go back to the first model, nope, that's not it. In the Bayes world, this is saying, yeah, let's not assume that n's at infinity. Let's go and sample with the n that we currently have. Right? So what I like about Bayes is, to me, we don't have to rely on the assumption that our sample size is large enough. And so this is part of the feature why people talk about Bayesian for small sample sizes. One of the problems with small sample sizes is that asymptotic convergence is sometimes slow depending on how complex your model is. Bayes allows for a little bit more uncertainty because of that. Yes?
So in this case, when we're estimating this thing, we have, for example, 4 parallel chains which are independent.
That's correct.
When we are analyzing the estimates, can we assume that those estimations affect the others? In this case, we change sigma, for example, and we have a new standard error for all the
The separate chain, so within a single chain, the estimation is tied together. So each of those are tied together. What we did to establish convergence allows us to pool chains together. So we're sort of having blocks of, if we were to think about it from a multi-level problem, any given value, any given step of one chain would be tied or dependent on those other values in that one chain. For us, though, because we converge to the same spot, we're treating them as if they were drawn from the same process. So it's a little bit more complicated when you think about it from the multiple chains. But that, am I answering your question? Or I think I'm hitting around it, but no.
Yeah, I have a follow-up question. So in this case, if we would decide, for example, to take one of those estimates out, for example, the beta height or one of the interactions, those values will change, right?
Yes, that's right.
Okay.
That's right. If we take an estimate out, now, if we take an estimate out in least squares, we take one of the parameters out, it will change also.
Oh, right.
And it will change also because in least squares, if there's some type of correlation amongst the predictors, right, there's this, it's the notion of partial and part correlation. The only time that when you remove a predictor that it doesn't impact others is if it has no correlation with the others and no correlation with the outcome itself, right? It's sort of, actually no correlation with the others, but a correlation. Anyway, I'm sorry. I'm rusty on teaching linear models. I got to trade classes to Lisa for a little bit. But does that help?
Yeah, okay, thank you.
You're welcome. Yeah.
I think I may be missing something in my head. So we set, I thought we set sigma?
In the second example, yes.
Okay. But then I guess for our visual, wouldn't sigma all be just one?
Yeah, it would be. This, I'm showing the plot of the first one here. Yeah,
Okay.
sorry. So why, so the answer to why, so I guess let me back up. The answer to why this is the result of the very first model where we estimated sigma in it.
Okay.
The answer to why our standard errors were different is because we are estimating sigma and allowing it to vary.
Okay, so in this code, is there one where you look at the plots for the second one?
Yes. Although I don't plot sigma because I actually removed it.
I plot sigma because it would be, okay.
Yep.
That is, okay, I feel better now.
Yeah, no, you're welcome. I apologize for not explaining that well. There's a lot of the same code that is only different by like one or two lines in this example.
I just wanted to make sure the sigma wasn't moving because that's what we said and I understood that, right?
That's right, yes.
Okay.
In the second one, it's literally set to as many decimal places as I could find in it. In the first one, it's set differently. Okay, so how are we doing so far? So feature one of Bayes. We don't rely on asymptotic convergence for our standard errors. That's cool. I think that's cool. It makes it harder to do analyses. If you think about power, although Bayesian power is a little bit different, power to do our analyses, not the same. It takes more effort to get a right result. So that's one of the things to think about.
What was that sentence? Don't rely on asymptotic.
Convergence. Like our standard errors that you see in least squares and in maximum likelihood, we make assumptions to derive those. And that assumption usually involves something as n goes to infinity, yada, 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 right? In Bayes, we don't have to make that assumption. We say, no, we are going to respect the fact that sigma is a sample statistic as well, add that to our model, have our uncertainty there. This actually shows up in interesting places in psychometrics. When we talk about item response theory, for those of you who are familiar with item response theory, we often talk about it as being a large sample type need, right? We need big samples to do like the 3-parameter model or the 2-parameter model. And a lot of times, the reason for that, in addition to being able to get our model to work, is what do we do with those parameters when we're done with estimating? We fix them at their most likely estimates, and then we go and estimate the scores for everybody, the thetas, the latent variables, right? We need the large sample, because the large sample means that we have small standard errors for our parameters, right? If we didn't have a large sample, and we didn't have a small standard error, but we were to fix it at one value, and estimate people's thetas, that uncertainty wouldn't be reflected in that estimate. So yes, I saw a light bulb or,
Well, I'm just thinking of like, there are some surveys in higher education that like would have decent sample sizes, like
Yeah.
20,000 people. Right?
absolutely, yeah.
And I also know of like more assessment type surveys and whatnot wouldn't have that power, so this could theoretically be an application.
That's right. That's exactly it. Perfect. Why? Sample size. Question online. I see. Sorry. Sorry for making you wait. I didn't realize that was what the hand up meant.
Yeah, no problem. I'm thinking for a scenario that if a researcher run like a linear model, a normal linear model, and his results didn't converge, so is it a good alternative to him to switch into Bayes instead, or as long as the mean squares doesn't give the significant results, Bayes didn't do that as well?
Good question. I think for linear models, most people would just, there are people who wouldn't say, let me switch to Bayes. They'd be, why are you running it in least squares in the first place? And so I think what you more often see are people who say, no, I want Bayesian because I want to incorporate prior belief, or I don't want to worry about asymptotic convergence, or for whatever reason, their philosophical underpinnings lead them that way. And for most linear models that we would try to make work, they will converge. They are not iterative. There is just one, like for a linear regression, there's one formula that you calculate and it's done. So unless you have a dependency in your X matrix, like if I go back, the formula we were talking about involves an inverse of this X transpose X. That actually is that in our estimates as well. If there's the only time that you won't get numbers is if this thing can't be inverted. That's the main thing. And so in that case, Bayes won't help you either, right? I guess Bayes may help you. You might be able to sort of put priors on some of the parameters, but you still need that term to be invertible. And so that won't help either. Did that help answer your question though?
Yeah, but in this case, is it better to get sigma estimated or fix it to what's the mean squared?
It will depend on who you're asking.
Okay.
You ask me in a Bayesian class, I think it's better in a Bayesian sense because 30 people, with a sample, this data set has 30 people. It has a really good signal too. Like the R squared was 0.97, right? This is a really good analysis, simulated data. There's still a lot of error to it. So I would like to not rely on the idea that n of 30 is infinity to get my standard errors. I think it's better in a Bayes sense. But I take a more conservative approach to my analyses, and others will disagree with that philosophy. So that's my thought.
Okay, thank you.
You're welcome. So, yes. I don't want to persuade you. Like, you have to, it's tough. Like, there's part of me, I'm old enough now to, like, try to balance my opinions a little bit more. But, like, the younger me is like, yeah, Bayes is way better. Like, even if it's harder to reject hypotheses, even if it's harder to show effects, it's better because I don't have to rely on assumptions for standard errors. That's why I like it. So that's one reason. Even if I'm like agnostic when it comes to priors. All right, other questions? So speaking of prior distributions, you want to see the impact of priors? That's next. Let's talk about it. So do you remember what the default in stan is when you don't specify priors in your model? What does it default to? Uniform across the sample space of the parameter, right? In example 3, we will add a prior. I'm going to start with a prior for sigma. I'm going to start with 1 because otherwise I'm going to start adding lines and lines and lines of code, okay? So what is our prior for sigma? How do you pick a prior? That's the hard part. First thing I think about when picking a prior is what's the range of the parameter, because the distribution needs to match that range. I guess I can truncate a distribution, but I'd prefer a distribution that matches it. Sigma is interesting. Its lower bound is 0. Its upper bound is positive infinity. So there are quite a few distributions that follow that. So I went and I looked online. So this is one interesting thing. If you use JAGs, you don't actually specify a prior for sigma, you specify a prior for 1 over sigma, which is frustrating. So if you looked at my slides from my previous, or my handouts, or my R files from my previous class in JAGS, you'll see a different prior listed, because it models things a little bit differently. It's equivalent, but just a little bit differently. So I'm going to pick, I went to Stan's website, and I did some Googling, and someone mentioned that a nice, fairly uninformative prior for standard deviations is something called the exponential distribution. Has anybody heard of an exponential distribution? It sounds fun. It's got exponent in it, but really, let me do some Wikipedia-ing. Here's how I pick a prior. I go, okay, what's the range of the parameter? Range is positive numbers. What's the range or the support of the distribution? Lower bound of 0, upper bound of infinity. Check, that works. So I've got a good distribution in that it matches the range. The next question is, what's the shape of the distribution? How does it work? In particular, I'd like to know what the mean, how do we find the mean? So the distribution depends on one parameter, something called lambda, or a rate parameter. And the mean of the distribution is 1 over lambda, right? So if lambda were 5, the mean would be 1 over 5, or 0.2. If lambda was 0.2, the mean would be 5, right? So we know from our analysis, and we know from our least squares, that the most likely estimate, non-Bayesian estimate of sigma, was a little under 8, right? Like 0.7 or something like that. So if we were trying to be somewhat uninformative, we would not want a mean on our prior to be that far from 8. But more importantly, we'd like to know how variable our prior distribution happens to be. And that's where I look at the variance, right here. The variance is 1 over the parameter squared. So if I have lambda of 10, that means the mean is 0.1, and the variance is 1 over 100, or 0.01, really tiny. But if I choose a lambda that's a decimal number, like if I choose 0.1 of a lambda, then my mean would be 1 over 0.1, which is 10, and my variance would be 1 over 0.1 squared, which actually turns out to be 100. So if you're comparing the relative how much information is in each prior, that's an important thing to know, right? Where's the location, what's the mean of the prior, and how much variability is around it? Because I'm going to show you in example 4 what happens when priors go crazy. Like you pick really informative priors. How are we doing so far? So, yeah, question?
It's a silly question, but
No.
why is it I know obviously there's an e raised to negative lambda, and like when you said exponential, I was thinking like one of these.
Yeah?
And I'm like, oh no, it's this, and it's because like I mathematically understand why it's one, like because it's a negative exponent. I understand that, but why do we call it
Amen.
exponential?
Amen.
Yeah.
I'm going to say the same thing. Yes, right. Why do they call it exponential? It doesn't look like. I'm used to exponential curves going the opposite direction, right? I agree. Well, it turns out exponential distribution is part of a family of distributions called the exponential family, yada, yada, yada.
And it includes both positive exponents and negative exponents.
It's got all that stuff involved in it. And yes, so here's the thing I struggle with. Would you rather a distribution be named, and I'll be kind of blunt about this, for an old white guy, like Cauchy, right? Or F, which is like named for Fisher, right? Or would you rather it be some dumb name like exponential that doesn't fit it either? I don't know. But let's all agree that names get in the way of real math. And real math says, we're going to use this distribution right here. That's its density. But I wanted to do a little bit more investigation of this. So when you're picking a prior, you need to think about, like if you have a really strong belief or you have a real weak belief. I don't know about you, but I don't have many beliefs about this diet data going into it, apart from after seeing the numbers I think that's simulated, right? So I'd like to not put a lot of informative, like my bias in doing Bayes analysis is to do the least harm when it comes to priors. I prefer fairly uninformative priors to make things work. Now, fairly is a matter of degree, of judgment. But let's plot. What I do when I try to figure out a prior is I literally start making plots. So I'm going to take a hypothetical value of sigma that goes from 0 to 1,000 in 0.01 increments. Seriously, there's a lot of sigmas. Like R is, again, really struggling with that one. It's okay, R. Are you listening to me? Sorry. Seriously. There it goes. There are 100,000 elements of sigma there. I'm then going to plot an exponential with each one of these numbers, a value of lambda of 0.1, of 0.5, of 1, of 5, and of 10. And I want to see the shape of the distributions.
We're just like exploring this.
Just exploring it, right. Yeah, we're not applying it to the data yet. We're sort of shopping for a posterior distribution. How's that sound? We're considering the options at our local distribution store. So that is a plot. It would help to have a legend. So what do you notice about this? Lots of flat lines, but then one of these distributions gets really, really informative down at the bottom. And it turns out that's 10. Right? So where 10 is, we put a lot of mass there. So what that is going to do is it's going to weight our parameters to where the mass of that distribution happens to be located. So if we were to put an exponential of 10 on our model, we would expect our variance to start being pushed down, having this downward pressure applied to it, to put itself into this area. Similarly, if you look at 5, if you look a little bit close in here, there's little blue dots on that line. Those blue dots are for 5, right? So I did some zooming, and I zoomed in. Instead of plotting to 1,000, I plotted to 100. They still don't have the resolution. So I plotted to 10, still don't have the resolution. So I plotted to 5, and that makes it look a little bit better. Remember, the light blue line is 10, the dark blue line is 5, and then these are in order of magnitude. It's, what did I have here? 10, 5, 1, 0.5, and 0.1, right? So when you look at that, just think where the peak of that curve is what the likelihood is, or what the sampling process is going to push the parameter toward. So when I look at this, I will tell you that for most of the space of the parameter that I'm thinking about, the black line, exponential of 0.1, shows very little difference. Right? So no one spot on that line is going to be more favored than another. Each of the other lines have some type of tendency to push the parameter lower. So I picked 0.1. Other people will argue with me about it. In fact, almost everybody, if you're not a Bayesian, if you don't argue about the priors, I think. So that's probably not a Bayesian. I don't care. I mean, I care, I guess, but anyway. Yeah.
What's the advantage of using a 0.1 with an exponential distribution versus doing it uninformative if it is so flat?
Good question. There are some people who would argue about in certain extreme values of variance that you could lead to some weird results. Weird being variance kind of sticking to one of the boundaries, like 0 or something else. I don't think there's a big difference, personally. However, if you run this way, the people who tend to review this want to see a prior, right? And so, for whatever reason, even though the difference is probably trivial, saying I'm using an exponential with an uninformative prior makes people happier than saying I'm using what Stan calls an improper prior. And that sort of puts you in an easier area. So it's less pragmatic, it's more philosophical where the difference lies. Now, if I'm reading your paper, I'm totally cool with it without it. But I'm probably in the little tiny minority of those who do this, that think that way.
When you're reviewing papers, how easy or not is it to know whether or not they're thinking it's informative or uninformative?
It can be very difficult. It can be. So the only thing I can do And I haven't reviewed a lot, so most of the papers I review are about developing methods rather than using them. But in the times I have read them, or read papers, or better yet, in the COVID times, on the preprint servers, you'll see people doing a lot of Bayes analyses, and you're like, oh, I don't know the biology, but I can read the statistics. If I'm really confused about the prior is, I will take what they say and go plot it. Let me go plot the prior to see what it means. It says, this is my belief of where the parameter lies. And when the line is peaked, it says, I really believe it's here, right? So that's how I did it. Does that help? Other questions? So what do you think is going to happen when we run this analysis while I get it loaded up here? Should we see a big change between this model and the model that we ran with the uniform improper prior? Let's find out. First of all, first thing we need to check, convergence, things converge. By the way, the more informative your parameters, the easier it is in general, not in specific cases, but in general, to achieve convergence. So if you're having convergence issues, one of the fixes to it is to be more informative on the prior, because that extra weight to the likelihood makes the parameter a little bit more behaved. Usually what happens is, remember the posterior distribution is a combination of model and data likelihood times prior likelihood. If there's not a lot of information from the data or the model on the parameter, it's going to wiggle around a lot. It may not converge a lot. Putting that prior onto it forces it into a little bit more of a peaked range. And that's why more informative prior, because it multiplies the data likelihood, it moves the peak a little bit more to make it a little bit better to converge. For this analysis, though, convergence is not an issue. And for most linear models, it's very easy to get them to converge. So that's not our problem. Yes?
Does R give you a warning that it didn't converge, or do you always have to check?
Stan will, yes.
Okay.
Yeah. Stan will tell you not all things converge. In fact, I think I can trick this. One warm-up, 10 iterations. There it goes.
Okay.
Well, that's diverge. That's a little bit different than not converge. There it is. Yeah, they do give you warnings, although I don't know that they're what you want. Sometimes I can trick it to get it to do it. Yeah, it stands much more informative than like other Bayes packages about that. All right, let's first compare the results between the two. Okay, what am I comparing here? I'm comparing the model that estimated sigma with the uniform prior to the model that estimated sigma with the exponential prior. And the parameters are in the order of what I had entered them before, so intercept, conditional main effective height, and so on. That last row is the variance. So let's take a look at what we see. Model without the prior, mean and median are slightly different than the mean and median with the prior. Right? We've shifted the mean and median a little bit higher. Not only that, standard deviation without the prior is higher than standard deviation with the prior. Right? So the impact of the prior, because we only have 30 observations in our data, even an uninformative prior will shift the numbers a little bit. Right? Likewise, standard error or residual variance, 8.39 for a mean, 8.23 for a median, versus 8.22 and 8.09. What's that telling us? We have a little bit more certainty in our residual variance. And it's smaller. Right? So that's interesting. Would you like to see how it changes if I tighten the prior some more? Can you guess? All right, let me ask. Who wants to pick the prior? What's the lambda? What's the parameter value for the prior? I had 0.1 before. That was the black line. Here, you want to see the plus? I'm sorry? 0.5? Let's do 0.5. 0.5. So you'll note I just changed the parameter here. At the end of this, I just added some code today to talk about how we want to code this so it doesn't have to always compile. But that's coming. That'll be next week. Okay. What just happened? Okay, run the model. Always check convergence. Maximum R hat, still good. See results. Now what's happening? Not a whole lot different from the last time. These numbers look very similar. Did I run the model? Yeah, I did. So yeah, not a whole lot different between 0.1 and 0.5. Let's go crazy. Let's make it 10. That's just crazy. It's 5 o'clock here and I'm running Bayes analysis. It's like drunk on Bayes. Here we go. Convergence happened. Yes. All right, now look at that. Residual variance 8.39 here, 4.69 there. Now, what's interesting about this? All right, remember, the model parameters are yoked together in ways. We just put a prior that was very informative on the residual variance. That's like saying, I'm really confident that I have a high R squared in my model. That is a terrible idea for me as a statistician, right? I'm really confident that my model's good. Because now, look, our residual variance, or residual standard error, standard deviation, is much smaller than it was before. But simultaneous, even though the mean and median estimates for our parameters are not changed for our coefficients, like right here, 3.56, 3.56. Not a lot of difference. Where does that difference show up? In our standard deviations. Right? So now, all of a sudden, whereas before I said, look, Bayes is nice because you're not assuming asymptotic convergence. Bayes is evil because you can go and be really certain about some things and have that reflect in higher power. Again, power I'm putting in quotes. It's not a Bayesian term usually. But it's an idea that we have more information, less variability in our posterior estimates.
So what you're saying is we're walking a dangerous line.
Yes. Priors can make a big impact. And what we're doing right here, if you have a prior and you're not sure about it, is exactly what you're trying to do in a Bayes analysis, which is sort of what we call a sensitivity analysis, right? We're trying to see how sensitive our numbers are to a choice of priors. So it's an odd thing to think about, particularly when you're used to saying in statistics, particularly in linear models, there is one way. That one way is least squares. You get your least squares, and we built everything around that. It's fine. Here it's saying, I don't know, what's the prior? You said 0.5, I said 10. Who's right? How do we figure that out? There are answers to that I'll share next week. How are we doing so far?
Can you plot the OLS estimates against the 10, just so that the comparison is more clear?
You mean the mean value here?
Well, you had the mean and standard deviation of just like plain old linear regression against the Bayesian.
Yes.
Can you do that for the 10?
Yeah, I can do that too. Give me just a moment. Now, I won't have on here the error variance. I can only do up to the fixed effects, or the model. They're not fixed anymore. They're all random, actually. But, whoops. There we go. Nope. Hang on. There we go. All right, let me get some space to put this in here. All right, here we go. Is that what you're looking for?
Yep.
Least squares, Bayesian with an informative variance prior.
And that's why you don't like the linear statement that Bayes and standard errors are bigger.
Not always, right? It all depends on what you're specifying for priors, what you're specifying for how you do things. All right. Other questions on this?
I guess I'm trying to wrap my head around the code. So when you say the sigma and then exponential 0.1, the sigma has an exponential distribution. What does that 0.1 mean?
That 0.1 is called a hyperparameter in Bayes language. It's the one, so each distribution is going to be described by a set of parameters. So the point one, that's why I had to look up Wikipedia. I was like, what is the parameter? What does it mean in that distribution?
It's that lambda?
It's the lambda, that's right. And technically speaking, that's a really good question, because when you think about a distribution, if you're new to Stan and haven't used it much, like I'm fairly new to it. I mean, I've used it on the periphery, but not enough to like know the full details of it. Always look at the user guide, the function reference. I have a link on the website about that. Because sometimes these distributions, they change how they're parameterized. Right? A beta distribution or a gamma distribution may have a 1 over the parameter sometimes instead of the parameter itself. So you go in, you look at the function reference. Here. let me show-
Okay, so that all depends on what distribution you're looking at. And
That's
then you
right.
have to look at that distribution and decide,
That's right. So here's how I did it. I went to the functions reference.
yeah,
On the functions reference on the left-hand side, you see distributions. There's positive continuous distributions, and I went to exponential. And it told me, I'm sounding like my son even more. Exponential of beta. Now, even though we called it lambda, of course they call it beta, but then they give you what's supposed to be the likelihood function for it. If I go up and look at the distribution in Wikipedia, I want to map that same density function. The density function is parameter times e to the negative parameter x. It's parameter times e to the negative parameter y in this case. So these are the same distributions. This means the same thing as I was calling it before, but you have to pin it down.
okay, so then the default code is that it just is uniform?
Uniform.
And there's no number there?
No number. Every parameter, every value is equally likely, is what that's saying. So if we were to draw a line on it, you'd see a flat line across the entire parameter space.
Okay. I'm just trying to just make sure that I understand, like if I chose something other than exponential, how would I know what number goes there?
Good luck. Trial and error. Well, that's the thing. So that process that I just showed you where I went and I plotted the distribution is how I'd start. I'd go and I'd take a look. I'd figure out what the mapping of the parameter was. And I'd see what the function in R is and make a plot of it. And then go, what's an uninformative version of this parameter? How to do it. Now, it sounds really complicated. And it is. But a lot of the parameters we will use are very regular and routine. So when we get to factor analysis, a lot of what we'll do is very automatic. Right? Yes, every item will have a variance or a standard deviation. We'll need this. We might just use exponential for everything. Just keep it that way. You had a question?
Yes, sir. In this case, we chose this 0.1, but we do not have a specific number for sigma in mind. We are trying to plot our certainty or.
That's right.
So we have chosen this specific number, thinking about information, but not a specific value for sigma.
That's right. That's right.
And we also took into account this idea of mean or median for this specific distribution.
That's right.
Okay.
Yeah, it's tough because like we had the benefit of, this is a model where we could easily run it in least squares and see what's happening. Most models that we want to get into, we want to avoid doing that because it takes a lot of time usually, particularly in some of the multidimensional IRT models that are out there. So how do you specify a prior when you don't know what the parameter is? And that's why when we look at the plot of the distribution, I'm looking for me, if I don't know anything about it, I want it to be as flat as possible. That's my preference. Other people want more than that. Other people have some other prior belief, but for us, we may not. One question online, and then I'll let you go. Are uninformative, weakly informative, and uniform prior the same thing? Yes. Uniform is the most uninformative. It is every value is equally likely. Uninformative and weakly informative may not have every value be equally likely, but the difference between the most likely and the least likely is very small, like a very flat line. And then another question, is exponential distribution selection because of power? Graphs seem so similar. It's mainly because of convenience is what I go with. I saw somebody doing it online. There you go. Because YouTube told me to. All right, we're out of time. Thank you for your attention. Thanks for being here on a Friday. Thank you to everybody online, and I hope to see you next week. Do contact me if you have questions. So, see you later.
Will your office hours next week be Wednesday?
Yes, that's right. Yeah, sorry about that. They will usually be Wednesdays unless I